Hey everyone, so this is the title. I'm sorry for the clickbaitiness of it, but basically I want to talk about some non-standard uses of Ecto, both for database use and non-database use. But before I get to that, I would like to give some background, like answer why rather than just what. So yeah, I work at V7. I've been working there for the past 2.5 years or so. And we're trying to do like this all-encompassing machine learning platform where we let you annotate your data, or we try to find someone to do it for you, speed up that stuff, train your models, host your models for you so you can consume them via an API, and just generally improve the overall machine learning process so that basically anyone can use it and incorporate it into their product. So because of that, we have to solve a lot of problems. We have to deal with a lot of data. So our biggest tables are several hundreds of gigabytes now. We're expecting terabytes by this time next year. So just that alone is quite complex. Then we had a lot of complex endpoints because you need to be able to move items in your data set around, give them different workflows, copy things over here and there. So there's a lot of complexity there. And of course, since this is like a complex problem, people don't write tutorials for this stuff. So we had to figure a lot of these things out. And a lot of our solutions tend to rely on Ecto a fair bit. So as I said, both for database and non-database use. So before I continue, just this is stating the obvious, but since Ecto 3.0 or so, there was a split between Ecto and Ecto SQL. And yeah, so at least there is an idea of Ecto being used for other stuff, and we've seen that yesterday with Sasha's talk on normalization in the interface layer. There's a lot of blog articles about validating forms that aren't necessarily database backed, things like that. But we are taking this slightly further than that. What we will be using is for the non-database stuff mainly Ecto schema and Ecto chain set. I will talk about some Ecto query stuff that you can do, some stuff with multi, which I don't see a lot of content out there about it, and then just some basic stuff using Ecto insert and update all. And just another disclaimer, this of course won't fit everyone. We have a lot of things that we do internally and definitely not generalizable, but these sort of kind of are. It's still not just a plug-in solution. But the principle should apply to other problems as well. So yeah, it's not that weird. Use number one that I wanted to show is, Sasha called this normalization. As I said, we're taking this a bit more extreme and not as clear as his stuff, but I call it advanced param scrubbing and pre-validation. So what is the problem? We have a bunch of endpoints that tend to accept the same parameter structures. For example, an index endpoint has a filter key that is a map that is has a lot of internal keys. They all work differently. Some are just a simple value. Some are a list of values. So we match anything that matches anything in that list. They could be positive, so anything that matches. Negative, anything that doesn't match. Just a lot of stuff. And this can trigger branching behavior in our core logic. So there's a lot of complexity there. And then additionally, we have other core functions that could call these core functions as a step in their internal process. So we have to pass in these values manually as well, rather than just getting user input. So, and lastly, our endpoints, since they're public facing, the clients that use this, since it's complex, the more information we could give them in an error, the better, so they can use it more easily. So what we did is similar to normalization yesterday, a combination of Ecto schema and Ecto chain set, where we identify our structures, we define embedded schemas for them, and then we define validation functions, which are called from the endpoint as the first step. If the chain sets produced by these validation functions are valid, we return an OK tuple, and we use chain set.apply changes to get the original struct. If they're not valid, then we return an error chain set tuple, which we handle in a fallback and just render a simple 422 JSON, so the standard validation error structure, and that works out of the box. And then the additional benefit is that we get to pass that well-defined struct into our core function, and we don't have to deal with is this map of string keys, a map of atom keys, are the keys correctly formatted, anything like that. We know the struct is valid, and it just works. So yeah, I tend to forget examples when I do this, so I had to do like an item with the example so I can switch to my VS Code. So here we are. So to explain this, like this is an example repository. There will be a link at the end of the talk on the last slide. And I will add more to it. For example, it's missing the README now. But I'm really bad with like inventing example problems. So what this is basically an application that deals with pictures. A picture is a record that has a shape, which is a JSON-B column. It could be a point, so x and y. It could be a bounding box, so x, y with height. It could be a line, so a, b, which are points. And it could be a polygon, which is a path with a list of points in it. So that's what a picture is. It can have an optional name. It can optionally belong to an artist. And it could belong to one or more albums. So that's like, let's say this is a real world thing. It isn't, but it works for us. So to show an example of using this, I will go to the only controller we have. And we have two endpoints here. One is an index endpoint. The other is batch transpose, which is just some random batch operation that I tried to invent. But both of them deal with a list of pictures. And the way we define this list is by defining a filter in the params. And what we do here is, as you see, in the first step, we call validate batch params, which gets us an OK tuple with a struct. And then we pass that struct into the actual core function. So in a real world, I would probably split this, like Sasha mentioned yesterday, in an interface and a core layer. But here, like it's an example, so I just try to put it together to make it easier to follow. So we have these two. Let's see, one more. OK, let me just shrink this then. We good? OK. So validate batch params. I over-engineered this a bit. But yeah, we have an embedded schema, which embeds one filter schema. Because there could be other params here, in theory. They're not, but yeah, over-engineering. And then we have a validate function, which, as I said, it calls a change set. If the change set is valid, it transforms it into the struct and returns an OK tuple. If it's not, it just returns an error tuple. And then if we go to filter, which is where the core of it is, we have, again, an embedded schema with a simple field type, just a string, a couple of complex fields, so an array of strings. So that would be like matching if any of the array items matches the record. We have an embed, which has like some internal function logic of its own. And we have an explicit select all field. And that one is sort of, we tend to rely on that in our actual product. It's sort of like a way for the client to explicitly say, I want to apply this to all the records. I didn't forget the filter. So like there is a risk with things like this where the client could pass in like a blank filter, so we match on everything, or we have to handle that in some way, and they accidentally do something to all the items in their data set or something like that. So this prevents that. And like if we look at the bounds is another embedded schema. I define it here. It has like min x, max x. Like it defines a box, which is the bounds of an object. So we would filter on shapes that overlap with these bounds. And then it has some extra logic there to sort bounds. So if the customer, client, whatever, like does something like bottom left, point top right, we invert it so it's always top left, bottom right. So that's the kind of logic you can do this way. So that's the filter. And we can then, once we have it, we can then apply it using like just a regular reduce function. Each thing is applied differently. And when we get back to our controller, as I said, we just pass in the struct we get. And then the actual core functions are much simpler to use. So the index function is just apply the filter onto the schema, do a repo all, and then the batch transpose, I will just show the signature for now because I need the body of it for another example. So yeah, that's what it is. So back to our slides. Yeah, this is something we rely quite a bit on because we have a lot of these batch endpoints, and it allows us to, for one, like define the structures that we use in one place, keep them centralized. It allows us to easily validate these, to handle errors quite easily, and just generally, it makes refactoring that much easier because since we're passing the struct everywhere, any change is usually triggered immediately. If it's not, it's something that we need to fix and we tend to improve on when we track down a case like that. So that was use number one. Use number two is also something we rely quite a bit on. We would like to maybe do it less because there is like a hard limit on what it is we can do with it. But what it is speeding up batch operations using temp tables. What is the problem here? So some batch actions we do perform some very complex operations on the database. So it's not something that we do like just an update or just I don't know, some sort of aggregation or something. We have to get some data in step one, some other data in step two, get some data from our backend or from another source, merge with that, create some records, get the IDs of those records, merge with it, just basically join everything together to be able to like create some more rows in a table or update them or something like that. So it's not a one query thing. And generally, what we would have to do in most cases is resort to like loading the data into our backend, transforming it there somehow, and then pushing it back into the database. That works, but there's like a hard limit of how much you can do at once. So then you have to resort to, I don't know, chunking or something like that. But then you either do it in a transaction and you have to potentially deal with timeouts or lockouts or something like that, or you don't, and then you deal with some chunks failing. So it adds a lot of complexity. So what we started doing, and we, as I said, we do quite heavily, is we rely on Postgres temporary tables. So in Postgres, you can create a temp table using a temporary keyword, and you can set it to drop on commit. What we do then is we use Ecto multi. In a step in multi, we create the table, and then we run our other steps to join the data into that table, like aggregate everything. And once the data is ready, we push it to the actual table, commit the transaction, and the temp table is dropped. So this allows us to, in most cases, not have to pass almost any data from our backend to the database or in the other direction. We just pass plain queries, and it runs internally, and it just works. As I said, it speeds up our stuff quite a bit, so we will eventually probably still have to do these things asynchronously, but for now, we've moved that point where we have to do it quite a fair bit back. So yeah, example again. Not a great example, once more, because I'm bad with those, but let's try. Which one was it? I think this one. So, as I said, pictures can belong to an album. So we can add into an album, but there's like a random constraint there that pictures with a name, the name has to be unique within an album. So that's the example I'm using to do a multi. So this is how we tend to define our temp table. So it's a module, it's a schema module. You can give it, if you name your temp table, you can give it a name here as well. It doesn't matter that it's not always in the database. Ecto will still work with it for as long as it is. You define your fields. We tend to avoid foreign keys here because it drops performance a bit. And since this is all internal, we don't really need them, technically, in most cases. And then we tend to define the create table function within that module because quite often in our cases, we reuse the same temp table structure for different actions. So we keep it centralized that way in an external module, and that way all the logic is contained. And then we have our multi. So in the first step, we create our temp table. Then we do a insert into the temp table using the initial data, which is just a query. If we go here, just a simple select query on pictures, which applies our filter. So again, we're using like the batch param struct as a parameter here in the main function. Then in the next step, we clean up our data. So we eliminate those duplicate names using another query. So it's a multi-delete all with a cleanup query. And that query just uses a plain window function to just drop everything that isn't like the first occurrence of the name. And then the last step is copying to the actual table. So this is another insert all, and we insert into like a join table between pictures and albums. So again, a select query, very simple. And as you can see, like the only thing being passed into the database from the backend, other than the query itself, of course, is the album ID. Everything else is just copying data between tables within the database. So it tends to be a lot faster than anything that involves taking data from the database, modifying it, and putting it back in. And there is a caveat for this. In tests, since they're running a transaction, you will end up with, especially in tests where you call the same thing several times in a single test, you will end up with naming conflicts due to the table having like a specified name. You could do it. You could give it a random name, but then you can't really define a schema because you can't give the schema a name. So what we do, let me just find a test. I think it's here. So we just have to do this after every call. Not great, but since the operation is way faster for us, it's worth the additional work here, so to say. So we have this function, we call it after every call to an action. So that was example number 2. Trying to switch to the slides. Again, this is something we use quite often still, not as often as example number 1, but it is very useful for us. So yeah, we'll continue using it until for as long as we can. Example number 3 is something we don't use often. We have like maybe 1 or 2 use cases, but it's not a common knowledge thing as far as I know, and it's useful to know that it is possible. So what is the problem here? Again, we're updating a batch of records, but it's not, and again, it's not a simple update, but it's sort of a weird combination of where we're not doing like an operation, so like set x equals x plus 2 on all records. We're not setting a predetermined value, so we're not doing like set x equals 5. We're generally doing something where each record gets a different update, but it's based off of some sort of mapping or something like that. So a conventional approach, again, would be take all the data, apply the transform, push it back in. We could maybe use the temp tables from the previous example, but if you can, there is a simpler way to do it, which is you can actually join a table on a fragment that interpolates a list of maps in Elixir. So when you interpolate a list of maps, you get in the query a JSONB array. And you can then use JSONB array elements to unwrap it, so to say. And then you can join your table on this array and just do an update that way. So an inner join, perform the update, and that's it. So you just pass in a small subset of data, which is the mapping, and run your update. So this is by far the worst example I have. I was thinking of it this morning. There could have been so many better examples I could have done, but I'll try to explain one after I show this one. This is the batch transpose thing, and you'll immediately see why it's bad. So we build our new data by taking all the pictures from the database that match the filter. We run a transpose function, which is like a complex function in Elixir that we defined. And we map it as a list of ID, which is the picture ID, and transpose, which is the transposed original shape of the picture. Then we run an update query, which inner joins pictures on this interpolated data. So this is what you have to do. You have to like name your stuff. Not necessarily, but it makes it a bit more clearer to read. And we run the update on that. So we set the shape to data.transposed. And that works, but as I said, not a great example because it will operate on as many records as match the filter. So as many images you update, that many maps you're passing into the database. More appropriate example would be something like, let's say that the picture has a price or something, and you want to make an update where like you multiply the price by a factor, and the factor is based on type. So the type of the shape. So the type of the shape could be a point, a box, a polygon, a line. And there could be more types eventually. So what you would do is you would like get the unique types from the database, produce the mapping, pass that in. So that way you're like doing an update that updates, I don't know, 5,000 pictures, because that many pictures match the filter, but you're passing in 5 rows as this like JSON-B array. So that's where this works quite well. As I said, we don't do it often. We did it in a migration once. We do it in one tiny instance of like a core function, but like it's really tiny. But it does allow us to like do it in one query and really fast. So that was use number 3. Use number 4 is really simple, and I was really worried that I made a mistake this morning. So I stumbled into a conversation on joins on the Ecto repository, where they were discussing doing exactly this, like supporting this in the join macro itself. And it looked like they would actually support it, but then the conversation ended up with this isn't possible, and like it's hard to do for everyone, so let's let people do it some other way. So what is the problem? We filter in our application a lot. Like 3 use cases like are based on filters that I've already shown, and they are dynamically applied. So we reduce that filter query, filter struct, and do it our way. So some of them need joins, some don't. Some need the same joins, just random joins everywhere. But we want each filter function to be self-contained. We don't want to like have one function for filtering, another for joining based on those filters. We want it to be to run on its own without like additional complexity of figuring out which other things we need to run to get it to work. So what we did for ourselves, and this works for us because we have some conventions established, but we sort of wrote a maybe join macro, which will join only if the binding with that name already exists. So the convention that this works with is we have a rule, a strict rule, that if the same join, it always has the same name in our app. So that's why like the name is enough to figure out, okay, this is a duplicate join. If you're joining differently, but you're using the same name, this of course won't work. This is the link to the discussion I found out this morning. So yeah, I was worried I would have just 4 examples. I have 5. But let's show that example. It's really simple. It uses query has name binding. So basically, you receive the same arguments you would for a join. You check if the query has the binding that is specified. And if it does, you don't do anything. If it doesn't, you run a join on the query using those arguments. And just an example of how it works. So we have 2 filters for the artist. One is artist name, other is artist country. They work the same way, so they receive a list of of potential artist names or countries, and we filter if the picture's artist is in that list. And we use maybe join for both of them. So it's the same maybe join. In production, we would probably do it in a function, not just repeat the same code again. But what it allows us is, like, if we're filtering by artist, we just call this one function. We don't have to worry, does the query already have the join or not? We don't have to worry about anything like that. So yeah, simple example, but we use it quite often. And our last example, the biggest one, the one I had most fun with implementing, is something I call polymorphic embeds. There is a library that sort of does this, but it's missing one key feature that we needed that I'll mention. But just to define the problem. So our table, we have like our biggest table has a JSON-B column, and it's not free form. It's not a unique structure. It's one of X structures. So it's a polymorphic column. we need to be able to validate it because the data in there comes from different sources. It could be from our internal code. It could be from a client. It could be user input. It could be an import. Lots of different things. So we absolutely need to validate it because it's like our core table. If that has errors, we have a problem. And then we need those useful errors to be outputted to whoever made the call. So I did 2 solutions for this, namely because I thought the first solution, while simpler and clearer and easier to understand, wouldn't work with custom errors. I operated under that assumption, so I implemented both. And then later, I realized you actually can do custom errors with the first one. So yeah, I will show both, but to me, the first one is superior. I would use that one in production. So let's go to the example, just to not delay any further. So, as I said, first one simpler, second one more complex, harder to understand. Since the second one is actually worse, I will go with picture V2 for now, out of order, and just go through it. So we have a picture schema. It has a name and a shape. Name is not that important. The shape is a map. Since it's not a unique structure, it's one of X unique structures, we can't do an embed here. It's not possible, as far as I know at least. We have a chain set. We cast the params, name and shape. We make shape required, and then we call cast shape. And then cast shape calls build shape chain set. We will return to this after. But what build shape chain set does is it will try to extract the type field from the shape map. We have to cover both atom and string keys here. And then it will create a chain set using that type field and the remaining params. And how we do that is we just have a couple of clauses. We call chain set on the embedded schema that is that type of shape directly. And then like the schema itself is not that hard. The point is X and Y. Polygon is, as I said, a path of points. Line is A and B points, and box is X, Y with height. So those are quite simple. If you go back to this, what we then do when we have that chain set, where are we? Here we are. If it's valid, we again use apply changes to get the struct, and then we use a dump function which converts the struct into the underlying map. So the thing that goes into the database. The map is string keys, and again we define these dump functions on the schema itself for the shape. So it's just a simple mapping of a struct to a string keyed map. And we have to include the type because that's how we identify what the shape is. So the struct itself doesn't have a type field, but we know what the struct is, so that's how we get the type field that goes into the database. And that works. To get the errors out, so if it's invalid, we have a function called collect errors into map, and we store it as an error, as a validation error on the shape field using a custom key, extra errors. So you can pass in any custom key when you add a validation error to a chain set. Message is usually what you render directly. This extra errors is our sort of API, DSL, however you want to call it. So that's how we do it. So we have these errors. In the case where we couldn't produce a chain set because there was no type or something entirely different, we get a nil here, so then we just have a custom plain error message. And then when we get these errors, just to show collect errors into map, it's just a traverse errors that turns out the same thing we got in. So that's how we get a map. But just to show how we render these errors, I need to go into error view. So 422 JSON, we match on the struct. So if the data on the chain set is a struct picture or picture v2, we use a custom traverse errors function, which is not the cleanest thing I wrote. I'm sure it can be done better, but it works for now. And the output we get, if we go to just our test, here we are. So if these are the params, like this is a polygon, as you can see, first point is okay, second one is missing both x and y, third one is passing in strings instead of numbers, fourth is missing y, fifth is missing x, and we get this error output. So it's as if we just use the plain embed, except the embed we use is different based on the type of the shape. So it just outputs that without issues. So that was the V2. So the supposed to be better, but ended up being worse approach. And then V1, or V none, apparently, is using a custom Ecto type. So again, we have our schema. This one is being used for like other examples. So we have artists and albums, but those aren't important. We have a name, again, optional. And we have a shape, but this time it's of type pictures.shape. So that's a custom Ecto type, defined same as any other custom Ecto type would be defined. We need like a type function, which the underlying type is a map. That's how we store it in a database. We need a cast function, which we use when we're casting params using Ecto chain set. And like that cast function expects a stringed map with a type field in it, type key and a value. We have a schema module function which maps that type to a module. We could probably do it dynamically, but for this example works just as well this way. Probably easier to read. We need a we need a clause for the atom version of it. So if the map is atom keys, with just like this is not clean, but it's quick. We encode and decode to get a string key map back, and then call the actual cast function. And then we need an option where like the params are invalid. So yeah, the cast function, if it returns an OK something, then that value is successfully cast, and it's stored as like the change for the chain set. If it's error and a keyword, and that keyword contains a message key, then that message will be a validation error for that field. So we have two clauses here. One is we passed in a map, but it's missing a type. And the other is we passed in something else entirely. So those two are just working out of the box. And then, like the main one, we get the schema module. We cast that. So we use the same logic we use in V2. So just to show it, but a different function that wraps around that logic, so to say. So the cast function will call the chain set, so just the same chain set that we would in V2. And then it will call a resolve function, which, if the chain set is valid, just does like an OK tuple again. If it's invalid, we need collect errors into map, and again store it as extra errors. And that's really it. Same thing happens for every other shape. And that allows us to get a map from user input or somewhere, and we get a struct as a field value on this, like on the main pictures struct. So the shape will be the correct struct based on the shape type. And then we need like two more functions. One is dump to convert it to a stringed map to store into the database. So it's the same dump function I already shown. And one is load, which takes the string map and creates a struct. So that's what we use when you load from the database. And unlike the other version, the other approach, where like at some point it becomes a struct, but when you load the picture from the database, it's just a plain map with a type field and all that stuff, unstructured. And when you after you save it, it also becomes a plain map. In this case, when you load from the database, it actually becomes the struct you need. So you can match on the struct. And again, when you save, you also get a struct. So yeah, as I said, this was supposed to be simpler, but less powerful, ended up being the superior approach. So we're not using this. We're using some mishmash of both right now in our production, but this is probably what we'll be using very soon. And that was the last example. I was doing some thinking on this one, like, is it possible to do this with Ecto somehow? Unfortunately, as far as I can tell, the embeds and other like associations are like set in a macro. So they're set sort of like at compile time. You can't alter them dynamically in like on Ecto schema. So I guess it eventually would be possibly possible, but I'm not sure. It would require probably a lot of changes in Ecto and Ecto change set specifically to do this. Hold on. That's it. Any questions? Was it weird enough? Am I a bit short on time?
We have a few minutes, so
okay.
Let's see here. Where are we at? Are there any questions here from the audience? Okay.
Yeah, so this was really nice, and as you've said, it's like pretty unusual what you do, and there are not a lot of like people describing that. So what's your process, or maybe if you have any resources, but what's your process of like coming up with such a solution? For example, to use a temp table, or to use like this joining with data from memory. Like, how did you come up with that?
So generally, some people on our team are a bit more SQL heavy. So when we have a performance issue, we tend to like go raw SQL, and then from there we sort of like try to pull back into Elixir and try to do it like in a more Elixir way while like making use of this stuff. So with the temp table, that's basically what happened. We had some endpoints that were really slow. Then we did it with raw SQL, and then we moved it back to Elixir for as much as we could. Sorry, it's not there anymore. But yeah, you can't, like, there's no like create temp table multi-step or anything like that, but you can do it this way.
Amazing, thanks.
No problem.
Any other questions? I'm not seeing any questions online either, so let's give Nikola a round of applause. Thank you.